All right, so I'll just quickly go through these. We have a really good seminar series coming up the rest of this winter and into the spring. You can find that seminar series on our website, and also we've screenshotted here in the lower left-hand panel. We haven't had, we have speakers, but we don't have their titles yet, so that's where the TBD comes in. But you look at those next talks coming in by Luca and Jeff in March and April. And we have a really strong mailing list going on, but if you haven't joined it, please feel free to do so. And if you are interested or know someone who's interested in presenting at this seminar series, please feel free to reach out to us anyway. And Angélica's talk and all previous talks are on our YouTube channel, so you can find links to those. They're hyperlinked through our schedule, but also on our YouTube channel also. So I'll pass it off to Anthony, who's going to introduce our speaker today.
Sure, thanks very much. Just a quick reminder, please keep yourself muted unless you're asking a question. But if you have a question, feel free to ask during the presentation. Either raise your hand and we can make sure that you get a chance to ask it. But today we'll be hearing from Angélica Castillo. She's, I hope this is right, a PhD candidate currently at the German Research Center for Geosciences, or GFZ, in Potsdam, Germany. Her research interests are radiation belt modeling and data assimilation tools for space weather applications, and she's obviously going to be combining both of those to tell us about her recent work today. So thanks for joining us today, and go ahead, Angélica.
Thank you very much. Let me share my screen. Does it work? Can you see my screen?
Yes, looks good.
All right. Can you see also my mouse?
Mm-hmm.
Okay, wonderful. Okay. Good day, everybody. Thank you very much for having me. As Anthony said, my name is Angélica Maria Castillo. I am a PhD student at the GFZ Potsdam, and today I would like to talk to you about some data assimilation applications that we have developed for the radiation belts. Most of this work has been developed at the GFZ in Germany, also in cooperation with the University Potsdam through the data assimilation project SFB 1294. I would also like to thank Tomoko and all the organizers for inviting me to give this talk today. Okay, so today, first, I would like to introduce a bit our group at GFZ and a bit of my work, of what I've been doing. Then I will talk to you about some implementations of the standard Cannon filter for the radiation belt, and then some comparisons between the standard and ensemble Cannon filter implementation for the radiation belt. Then I will talk about a recently published study where we use a data assimilative reanalysis to intercalibrate satellite observations. Then I will briefly mention some other filtering applications that we have for other regions of the magnetosphere in our group. And then with some conclusions and outlook, I will finish my talk. So let's go into it. So I work at the Space Physics and Space Weather section at GFZ in Potsdam. We work with Professor Yuri Spritz. This is our lovely group, and we are located at the heart of Potsdam in a very beautiful campus. So if you ever had the chance to come and visit us, you're very welcome to do so. In our section, we try to understand the dynamics of particles inside the magnetosphere. We try to understand the evolution of ring current plasmasphere and the radiation belts, and how this can lead to hazardous levels of radiation. We also try to specify where these high levels of radiation will occur, where and when, and we develop tools to forecast them and to provide a service to the community to avoid calamities that that could damage our spaceborne and infrastructure and also terrestrial infrastructure. The main focus of my research, as my title already says, are the radiation belts. I focus particularly in in the electron populations in the outer radiation belt, which are highly energetic electrons that are very dynamic and show changes in time scales of minutes to hours. For this particular system, we have two main sources of information. One of them are satellite observations. We mostly use particle fluxes. We also have magnetic field observations and wave observations. But we can also model the evolution of phase-space density using a Fokker-Planck equation. And then we can transform particle fluxes using the formula framed in purple. There are several satellite fleets giving us observations of this region. So we have satellites at very different orbits, providing different energy spectrums. Some of these observations are pitch angle resolved, some are not. Some of these satellites use different instruments to measure radiation in space. But still, because of the vast region that we're observing, these observations are still very sparse. In order to model this region, we use the VERB 3D code, the Versatile Electron Radiation Belt code that was developed by Yuri Spritz in 2007. This is basically a three-dimensional Fokker-Planck diffusion equation that basically describes the evolution of electron phase-space density in time. The main equation has three terms. The first term, framed in blue, describes radial diffusion. The second term, framed in red, describes energy diffusion, which leads to local acceleration. And the third term, framed in green, describes pitch angle diffusion that causes precipitation of particles into the atmosphere. Depending on what dynamics of the system you want to resolve, sometimes you can go by using very coarse grids, but if you want to, for example, resolve mixed diffusion, then you have to use very, very fine grids with dimensions of 100 to the power of 3, which is really large and becomes very computationally expensive. So the issue that we have with the satellite observations, as I already said, is that they are very sparse and we cannot fully observe the system. The issue that we have with the physics-based models is that we cannot reproduce the system in a laboratory, so we don't really know how accurate our models are. So ideally, what we want to do is we want to gather all the information from these two different sources and combine them in an optimal way so that we get the best possible approximation of the system, right? And this we can do using data assimilation. Basically, data assimilation allows us to blend the observations and the model state using a filtering algorithm that will update the model state and even will allow us to forecast in a more accurate way. Data assimilation does this by accounting for the uncertainties in the model and in the observations. It will allow us to reconstruct the entire state of the system, and this is very helpful to study past anomalies in the system, for example. It also allows us to get more accurate initial conditions for predictions, and this leads to a more accurate forecast. And from a scientific point of view, we are hopeful that it also allows us to find information about missing processes in our physics-based models. The most known filtering algorithm is the standard Kalman filter. which basically uses the assumption of Gaussian distributed observations and states of the model. It also uses the assumption that the errors are Gaussianly distributed, but here it's very important that you have to have a guess, an initial guess of the distributions of these errors. Then you can blend the observations and the model by following two sequential steps, the forecast steps, which will basically evolve your model in time. And then the analysis steps, which basically accounts for the covariances or the errors of the system and of the observations, and will combine them in an statistically optimal way to provide the updated state of the system, basically. It is important to say that the standard Kalman filter was actually developed for linear systems. So in this case, you always have to linearize the operator of your model. So you have to linearize the operator of the that solves the partial differential equation. One of the main issues with the standard Kalman filter is the estimation or the evolution of the covariance matrix. I have framed that below here in red. So basically, you give the algorithm an initial guess of your errors, and then the algorithm will compute the following covariance matrices using this formula, which means you have to store and operate these metrics every time step. If you are using small grids, as I said before, if you're using small grids, this is a very, very nice thing to do, and it's not computationally expensive at all. But if you're using high grids or high dimensional problems, this becomes an issue. For this reason, in 2013, Professor Spritz implemented, in order to try to get around this issue, he implemented the so-called split operator Kalman filter, which basically assumes that if your time step is small enough, you can basically approximate your the multidimensional operator of the partial differential equation. You can approximate it as the sum of two linear diffusion operators. So in this case, in this example, in the formula that I show here, this is a two-dimensional operator. So we have two linear diffusion operators. But in the radiation belts, we have a three-dimensional model. So basically, you would have the sum of three linear diffusion operators. And then what you would do in the split operator Kalman filter is that you would apply a one-dimensional standard Kalman filter to each of these operators in space, and then you will evolve it in time. Using this initial implementation of the split operator, we were able to make initial long-term reconstruction of the radiation belts. This is a study that was presented by Sebastián Cervantes in 2020. So in the upper two panels, you see the evolution of electron phase space density for a time period of 4 years. I don't know if everybody is familiar with the format of these plots, so let me just briefly explain them. So the first panel presents in the x-axis is time, and the y-axis is L star, which is a magnetic adiabatic invariant of the radial distance. And in the first panel, we see the observations of Van Allen probes and GOES. Color-coded is the electron phase space density for that period of time. Those observations were assimilated into the verb code using this split operator Kalman filter, and the results of that are shown in the second panel. This is for fixed mu and fixed k. These are also adiabatic invariants. So panel A and B are for one fixed mu and k, and panel C and D are for a different mu and k. This is higher energies, higher pitch, same pitch angles, but higher energies. Oops. And in panels F, in panel E, we show dynamic pressure. Panel F shows Kp and VST index. Additionally, using this initial implementation of the standard Kalman filter, we were also able to perform initial parameter estimation studies. This implementation also allowed us to develop a real-time forecasting tool for the radiation belts that runs every hour at our website on GFC. This implementation uses a realistic Siganenko model, a magnetic field model. In the upper two panels here on the right, you see the real-time observations that are provided by Goes and Arasi. These observations are assimilated into our Verb 3D code in real time. We produce a reanalysis of the past 7 days. And then we issue a forecast of the radiation belt system for the coming 2 days. These predictions are based on machine learning predictions and empirical predictions of space weather, solar wind parameters and the Kp index. Oh, so we have been able to achieve quite a lot using this split operator implementation, but we wanted to move to some algorithm that would allow us to make probabilistic predictions. And in this case, the ensemble Kalman filter is the algorithm of choice. Here you also use a Gaussian assumption for the distribution of errors, states, and observations. But in this case, you don't have to know the distribution of how exactly this distribution looks like. What you're going to do is you're going to sample those distributions by perturbing observations and state using some sequence of noise, for example, white noise. And the assimilation occurs again in 2 sequential steps, the forecast and update states, which are pretty similar to the standard Kalman filter. But the ensemble Kalman filter is an approximation of the standard Kalman filter. Basically, it is based on the calculation through ensemble, through sampling of distributions. It uses the, you can calculate the first and second statistical momentum, and then the solution, assimilation solution of the ensemble Kalman filter should converge to the optimal solution of the standard Kalman filter for an infinite number of ensemble members. One of the most convenient parts of the ensemble Kalman filter is that the algorithm approximates the covariance matrix, which, as I told you before, when you're using very large grids, becomes a huge problem when using the standard Kalman filter. So in the ensemble Kalman filter, basically, you can approximate the covariance matrices using these 2 formulas in the bottom. And then you just calculate them once per time step. You do have to operate them, but it's only for the estimation of the updated state. But then you can dismiss them and you will calculate a new one for the next time step. So this makes this algorithm a bit more computationally efficient than the standard Kalman filter. And it also allows you to use diffusion operators that are not linear. So you can also apply this filtering algorithm to highly nonlinear systems. So we wanted to test if we can create an implementation of the ensemble Kalman filter for the radiation belts. And if we wanted to test if we can assure convergence of the ensemble Kalman filter solution to the standard Kalman filter. So Indeed, with this very technical slide, I will try to explain you how we have set up our ensemble Kalman filter. Basically, in order to be able to compare the two filters, we first set up the Kalman filter because the ensemble Kalman filter is just an approximation of the standard Kalman filter. So we set up a simulation of the Kalman filter that will use 50% standard deviation. The covariance matrices of the model and the observations are estimated as the standard deviation multiplied by the state or by the observation and then squared. The initial state of the system will be the steady state solution of the diffusion equation. And then similarly, in order to set up the ensemble Kalman filter, we create a covariance matrix of both observation and model that will converge to the covariance matrix of the Kalman filter for the limit of infinite ensemble members. This covariance matrix uses a sequence of white noise that looks like this. And uses the same standard deviation as we use for the Kalman filter. We evolved the state of the ensemble of states using the approximation given by Evanson in 2003. And then we also use the steady state solution as the initial condition, but we perturb it using this sequence of noise in order to create the first ensemble, the first ensemble. Could it be that there is a question? I see something in the chat. Okay.
I just said that the theory doesn't support that ensemble Kalman filters support highly nonlinear observation operators. So I have some stuff on this I can send you after the meeting, but I'd like to just let you keep going. But I disagree with that statement.
Okay.
Yep.
Thank you.
Please let's ask questions at the end so that can stay on time. Okay, go ahead.
Okay. Yeah, but thank you for your comment. Oops. All right. So in order to test our setup for the ensemble Kalman filter, we used a controlled environment. We developed a synthetic experiment in which basically we create a true system, a true state of the system, which is shown in panel B. We run the verb code using fixed parameters, fixed KP, and then we run a synthetic satellite through this state of the system. We extract data points, the blue, the white bubbles. We extract data points just as a normal satellite will measure the system. And then what we want to do is we want to assimilate these observations into another simulation of the verb code, which is shown in panel A, which is run with different parameters and looks completely different to the true system. We want to assimilate those observations using both the split operator Kalman filter and the ensemble Kalman filter implementation setup that I showed you before. The assimilation results with the ensemble Kalman filter are framed in blue here on the right. And then the assimilation results using the ensemble Kalman filter are shown below for increasing number of ensemble members. So we have 5, 40, 150, and 1,500 ensemble members. And then at the very right, we show the difference between the assimilation results using the Kalman filter and the ensemble Kalman filter for each different run. So what we basically observe is that the difference between the assimilation results goes to 0 when the number of ensemble members increases, goes to infinite, basically. And this is the mathematical proof that our setup is correct. So of course, you don't want to run 1,500 simulations. So we estimated the absolute analysis error, which is basically the difference between the true system and the assimilated result of the Kalman filter and of each ensemble Kalman filter simulation. The absolute analysis error for the Kalman filter run is shown by blue diamonds, which by the blue curve, let's better say by the blue curve. And when you look at the absolute error using 150 ensemble members, which is the red curve, you already see that these are very close to each other. And so we came to the conclusion that using 150 ensemble members is sufficient to reproduce an optimal solution of the system. Using this setup and 150 ensemble members, we also perform a simulation of real satellite observations for the radiation belts. In the first panel, I show observations of GeoDAWG and Van Allen proofs for a period for the month of November in 2012. The second panel shows the assimilation using the ensemble Kalman filter for 150 ensemble members. And the third panel uses the assimilation results using the Kalman filter. The fourth panel is the difference between both simulations, which clearly shows that the differences remain in the negligible side of things. The last panel is the KP index, just to show that we have enough activity throughout this period. So all in all, we have been able to implement successfully the ensemble Kalman filter for the radiation belt system. And now we move to a different application which was recently published in Space Weather. In this application, we were trying to answer the question on whether we can use data assimilation to intercalibrate satellite observations. This is motivated by the fact that most of our observations, or basically most of the satellite observations that really observe the heart of the radiation belts are a highly elliptic orbit. And most of the codes that we use have the boundary at 6.6, so at GEO. And these are the observations that are that have the most quality for us. But we have tons of data from LEO satellites, it's fast orbit. So we have tons of observations at LEO orbit. But at LEO orbit, we only observe the very, very edge of the system, right? So this leads to a great discrepancy between observations when we compare them. So in the upper panel, I am showing the observations of NOAA 14 for fixed energy and small pitch angles. LEO satellites tend to only deliver small pitch angles, observations at small pitch angles, but they have a great deal of observations. So we wanted to find a way to be able to intercalibrate all of these observations in an easy manner. So traditionally, we use phase space density matching, which is based on Liouville's theorem. And for this, we need to use spatial or geomagnetic satellite conjunctions or on-orbit comparisons, which really constrain a lot the data that we can use. So we were wondering how could we improve intercalibration of satellites? And for this, we could use, again, the tools that we have, all the observations and the physics-based models that we have, all the information of the system, right? And then get the best possible approximation of the system, a so-called reanalysis, again. And then once we have the reanalysis, so in this case, in panel C, I am showing a reanalysis that was run using Van Allen probe observations. Once we have this reanalysis, because a reanalysis is a full three-dimensional reconstruction of the system that evolves in time, basically what you can do is you can compare how this system compares to what your observations look like, and then rescale your observations. So basically what you could do is you could fly your satellite through the reanalysis, estimate how the observations in what the satellite observes in the reanalysis and compare it to what the satellite observes in reality. And then you can perform statistical analysis of these phase space density ratios or flux ratios, and then you can estimate recalibration coefficients. In order to validate this study, because this was the first time that we were doing this, we also perform a traditional conjunction study. In this case, we used 6 missions of the POES fleet for a period, using data for a period of 1 year. We only use the 90-degree telescope because it's the one that observes mostly trapped. And we use the data set that was delivered by PEC in 2014. We flew our satellite. We fly our satellite through the reanalysis, and then we perform on-orbit comparisons at satellite location and estimate these flux ratios, obtaining over 23,000 points with which we can work for the intercalibration. From the conjunction study, though, even if we use both satellites, Van Allen probe A and Van Allen probes B, we only obtain a bit over 2,000 points, which means we get an improvement, a tenfold improvement in the data that we can play with for the estimation of intercalibration coefficients. This will clearly be seen in the statistical analysis of the flux ratios. As I show here, in the left, you see the distributions of the flux ratios that are obtained from the on-orbit comparisons from the reanalysis. We observe nicely bell-shaped distributions with clear peaks. And on the right, you see the distributions that would be obtained from the conjunction study, from the flux ratios obtained from the conjunctions. These distributions look a bit wonky, and the peak is not always very clear to, not very clearly observed. We also analyze other parameters like ELSTA, the distributions in ELSTA, equatorial pitch angle, and geomagnetic activity, KP index. Here I only show ELSTA for the sake of space. But here again, clearly from the reanalysis, due to the large amount of data, we obtain nice distributions with clear peaks, where we can easily estimate the median and the maximum absolute deviation. While from the conjunction study, sometimes we're forced to work with beams that have less than 10 points, and the distributions are really not very friendly for intercalibrating. So at the end, what we do is basically we estimate the median of those distributions, and from there, we estimate the intercalibration factors. Framed in blue, I show the median of the flux ratios that were obtained from both the reanalysis and from the conjunction study. And the similarity between the results is just striking. So basically here this is the most important figure of the whole study, actually. In the end, we have our final recalibration coefficients are given in not only in terms of energy, because they also depend on L-star, but at the end, our curves are way more smoother than the curves that you will obtain from conjunctions, and the recalibration coefficients are more trustable because we have more data. Additionally, the reanalysis, because you obtain so much data, you can use a short-term reanalysis to intercalibrate a large number of data sets. And so this was a very fun study and was a very nice thing to do. In our section, we also have developed different data assimilation applications for other magnetospheric regions like the ring current and plasmasphere. So my colleague Bernhard Haas has recently published a validation of data assimilation for the ring current using a convection model. Basically, he assimilated ARASI data and then flew Van Allen probes through the reanalysis, and then compare the real observation of Van Allen probe with what the flyby would from the reanalysis would obtain, and his results were very accurate. Additionally, in the past, Irina Yelevskaya developed a combined approach that allowed, that improved her neuronal network for the plasmasphere. Basically, she was trying to solve the problem that neuronal networks, neural models for the plasmasphere usually have very few training data sets with high KP, because there was not much high KP during the Van Allen probe era. So when the neural network had to perform during storms, it would perform very bad. Oh, let me see if I can run it again. So when the neural network had to perform during storms of high KP, it would perform very bad, while a physics-based model would give better insights into what happens into the plasmasphere. So what they did was assimilate the observations from the physics-based model into the neural network, and the assimilative model would give then very results during storms. So this was also a very, very interesting approach that they took in order to solve this problem for neural networks. So yes, here I reach my conclusion. So in general, we have implemented quite a few interesting tools for the radiation belts. So in order to solve the problem of the high dimensionality of the radiation belt for the Kalman filter, we have implemented a split Kalman filter that allowed us to generate a real-time forecasting tool for the radiation belts. Additionally, we were able to implement an ensemble Kalman filter, and we were able to prove convergence to the optimal solution of the Kalman filter by using 150 ensemble members. We developed a new intercalibration approach for satellite observations using data assimilative reanalysis, and this assimilative intercalibration approach allows us to use short-term reanalysis to intercalibrate larger data sets. Well, we have already developed quite a few tools for the radiation belts. There is a lot of still to do with data assimilation, and so we are very excited to try some of these methods for other magnetospheric regions. We are also looking forward to try to implement some other ensemble-based filters for the radiation belts, because at the end, the ensemble Kalman filter that we implemented didn't turn out to be so computationally efficient as we thought, for example. But yes, in general, that we're still in the infancy, I mean, of data assimilation applications, and hopefully with increasing number of observations, our data assimilative results will be even better. So thank you very much for your attention. With this, I conclude my talk.
Thank you.
Yes, thank you very much. Okay, we have some good time for questions. I guess we can start with Jeff's.
Oh, yeah. Well, it was just a technicality and it really didn't matter for much of your other presentation. But when you mentioned that common filters support strongly nonlinear observation operators, there's quite a bit of research. And I mean, just the theory shows that that's that's not the case. So I'll be happy to send you a few papers just to help with that particular misconception. So like I'm sending a paper now that says how to handle nonlinearities and ensemble common filter. And some of the approaches are yeah, as you mentioned, like hybrid schemes that will take advantage of the good things of ENKF as well as the variational methods to do like a direct minimization. Or there's been some work on doing iterative ensemble common filters. So there's one by Sakhoff that I sent as the first link called the iterative common filter. And the second one is called the running in place method, where you basically just keep trying to resolve that nonlinearity. And there's some just like 3 variable Lorenz models that they test these on, but the results have been shown for larger models as well. So just wanted to clarify that when I saw that that's what I did my PhD research on. So I just felt I had to clarify that, but it really didn't impact your talk much. So it was more technical than anything else.
All right, thank you very much. I will definitely look into it.
Great. I can read out John's question as well, unless he'd like to say it himself. Basically, can you elaborate on why the ensemble common filter would be more computationally efficient than the standard common filter? Intuitively, I would expect an ensemble method to have a greater computational cost because of the need for multiple model executions and the need for the filter code to operate on multiple model states. Yes, so this is partly true. So indeed, we were hoping that well, this is the thing. So we can only compute the solution for the full standard Kalman filter, for the full 3-dimensional Kalman filter. Oh, that's not good.
Oh my goodness, I think Angélica.
Oh, that might be it.
We know what happened. We got shut down.
That wasn't very much warning from the computer.
Yeah, I know. Like, I think she will get back, and then, yeah. So,
like I said, I did a lot of my PhD work on this. So the ENKF is not necessarily more computationally efficient than the common filter, but the problem is with the covariance matrices. So the covariance matrix, if you have a very large state space, then you have to have the square of that state space. So let's say you had 10 to the 6 variables, now you need 10 to the 12th in the covariance matrix. So that could be just a killer for data assimilation. So if you use an ensemble common filter, you can invert those covariance matrices and work with them by basically doing a sample covariance estimate. So that's where it becomes more computationally efficient.
let's see. Yeah, thank you, Jeff. I feel hesitant to go on discussion without speaker.
Yes, I think we keep the Zoom room open for a bit longer in case she does come back.
If you have, please, maybe you could put additional questions in chat so that you can queue up some questions. Any other questions, please? Looks like a paper just came out. It says 2004. Let me email her and see what's happening.
She just came back in to the room, it seems.
Oh no.
Cannot unmute.
Okay, so you cannot unmute. I see. Maybe Anthony, you can unmute, huh?
I can click ask to unmute, but I can't unmute for her. That's strange.
No. I guess Angelica was responding to John's question.
This has to unmute. I can click ask to unmute, but I can't force you to be unmuted. I can make you a co-host and see if that changes anything. That does not
Oh,
do that
that's
either.
weird now.
There we go.
Okay.
Yes, sounds good.
Oh my God, I apologize. My computer just crashed.
Do you want to continue responding to computational efficiency?
Yes.
Okay, go ahead.
So yes, so this is true. We were thinking the thought behind this is that the main problem when we calculate, we try to calculate the standard Kalman filter for the radiation belt, is the covariance matrix, because it is so large for large grids. It's really impossible to use it. So what we wanted to do was use the advantage, take the advantage of the simple implementation of the ensemble Kalman filter, the simple estimation, simple approximation in the ensemble Kalman filter in order to estimate the covariance matrix. So in that sense, we were hoping that this was going to be more computationally efficient, and we did achieve some computational efficiency. So for 150 ensemble members, indeed, you can pretty much run at the same speed. You can run the ensemble Kalman filter pretty much at the same speed as you would for a two-dimensional standard Kalman filter. So that is true. But it was not as efficient as we thought at the beginning. So this is,
Angelica, could you could you explain if you localize covariance in an ensemble filter? Did you have to usually in a ensemble Monte Carlo method, we we have to do something about covariance, either localize and then also inflate. Did you have to do those?
localization or inflation? Well, we tried to do this, but this is a bit of a tuning work, I would say. So for the paper, we didn't do it because we just wanted to present the main implementation. We have tried some simple localization and inflation, but it turned out to be not very efficient, so not very good. So when you do that, basically you do good in some places and then you do very bad in other places where you were doing well before. So I think Umberto Godinez showed already that the best method that you can use is a dynamic inflation, and yeah. So we were hoping that it was it was possible to do some simpler approach for this, but no, we couldn't.
And earlier, Jeff, sounds like he's studying filter, had a question about nonlinearity, and then so there's a list of future work that you had at the end. So where do you think that you in your group or in your work you wanna kind of dig into maybe for your work, that you know, is it nonlinearity giving you a headache? That you see that what headache means that, you know, that if you choose a method that capture nonlinearity of dynamics, or the relationship between state and observation that you have, you know, like what's your sense in terms of where what is the best investment maybe for you and then for the community for the radiation belt? It's a good big question, but you know, like we were learning together. So if you could share your experience.
Well, it is very complicated to talk about uncertainty when you do not have a full understanding of the system. You cannot really see it. I guess for ionosphere, you have a lot of observations. This should be a more, I mean, I wouldn't say easy, but it's a task that at least makes more sense. But for radiation belts, this is really not the case. So what we're trying to do, what is interesting for me at the moment, is try to validate the forecasting tools that we have. So does our data assimilative model, does it produce something that is meaningful in terms of prediction? This is something that I am particularly very interested in. Also in terms of mitigation of hazards. This is a very important thing at the moment.
Any other thoughts? Yeah, thank you. I think I found your space weather paper very encouraging. Yeah, I'm gonna take a look. I posted that. I hope that's the right link. Any other thoughts from the audience, please? We have time.
Or can I ask Jeff to post the links again, because I
yeah,
see the
sure.
the older. Chat.
Actually, what's the best email for you? I'll just email you some things.
Yes.
Is it gfz@potsdam.de?
That is correct. Yeah.
Okay, I'll email you there then.
Let me write it in the chat.
You know, so it's just because we have time, and then I really want the community to discuss, and I found it interesting because I see Grant on the audience that, so it's going to that kind of reducing a, you know, state space, and then, you know, the magnetospheric data simulation or data fusion work, and then it looks like, you know, in your group going, okay, let's use the full, you know, like as a, you know, nonlinear model, and then use a filter. So I found it very curious that how this sort of, to me, like two different thoughts and to this approach that going forward. And then I'm curious. I mean, I'm sure there's advantage and disadvantage, and then any other. I'm not the one who practice data simulation and magnetosphere, but I don't know if any thoughts.
I mean, I guess ideally both can offer some sort of solution, no? Reducing dimensionality is always a good idea, at least to, you know, to get some insights into what is happening in the system. But also, I mean, we do not have as much data as, for example, the weather community. So this also makes our studies a bit harder. And for example, in this case, using machine learning methods is also something that, if we combine both things, I guess this is the future somehow.
I agree.
I guess I would just say that the data assimilation is pretty tricky, and the reasons for computational performance, a lot of times come down to the linear algebra aspect of it. And there's some tricks that you can use to speed up performance quite a bit. So one of them is the Sherman-Woodbury formula. So I'll put just the Wikipedia link. Sherman, it's also called the Sherman-Morrison-Woodbury formula. And it helps you to invert the ENKF much easier. So as opposed to inverting the entire matrix, you just invert. So there's multiple versions of this one. This one is for the rank 1 update, but so if you're just adding one observation at a time, but this one is one that will let you update the matrix more easily. So if you're not doing localization, this probably has a good chance of increasing your computational performance by quite a bit. But there's a lot of tricks out there that you can use to improve performance. So it might be helpful, and I'll just send you an email. We might want to go through some of these things to see where you may be able to get performance gains.
That would be wonderful.
Okay, sounds good.
Awesome. Well, if there's no more questions, let's please all thank Angélica again for a really wonderful talk.
Thank you.
And I would also suggest everyone to go please read her 2024 space weather paper that Tomoko posted in the chat, as well as her 2021 paper. They're all really great. So thank you so much, Angélica. We hope you guys all have a great rest of the day or evening if it's 5 p.m. at your time. And we look forward to seeing everyone in 1 month for our next seminar series.
Okay. Have a good day. Thank you very much.
Have a good day. Thank you very much.
Thank you.
Bye.